Hello, my name is Logan Scott, and I did a survey paper on machine learning usage in SDN-based intrusion detection systems. So I chose this area as SDN are the future of networking and allow a greater level of control. And I was interested in the current state of. I wished to form a taxonomy and identify current challenges as well as focuses and any promising results that there might be. As for the scope, I wished to be fairly comprehensive, so I chose to look at the various branches of machine learning algorithms and how they have been used in intrusion detection systems within SDN. And so I also only focused on network intrusion detection systems, NIDS, rather than also HIDS, which is like on a per device basis rather than watching over the whole network. As for comparison metrics, I chose accuracy, false positive rate, which is important to minimize because false alarms will decrease the trust in the IDS. And speed was also a metric. I consider the dataset used. The attack categories is trained on the feature selection and how that was done, whether it was manual or assisted by a machine learning algorithm. And I focused on two main areas of NIDS: Internet of Things implementation and just traditional NIDS. And I also was comparing based on the type of algorithm used, like where it falls on the taxonomy. I also focused on the author's motivation and goal through the research, whether it was minimizing the false positive rate, maximizing accuracy, or another. I noticed that there was a preference with using the NSL-KDD dataset, which is a massive dataset that was basically pruned from a larger one released in 1999 called the K-Cup 99. And that had some problems with bias and duplicate data entries. So that's why it's not really used anymore, and that's why NSL-KDD was created. And usually there are around 6 features selected on average when done manually. And the detection rates have been seen approaching 100%, although getting that with a low false positive rate is difficult because I also noticed that no alternatives to the OpenFlow protocol were used, and some articles felt like they were leaving out important information, such as like information about false positive rate. So mention one positive end but not the other negative end, although most were consistent with that. And as for minimizing the false positives, there were some promising results. One, with using an ensemble model, they were able to get it down to 0.03% false positive rate, but that was also with 80% accuracy, because you have to be more picky. But then we are good now with. There's also a more promising result in that the two with recurrent neural networks, and they were able to get a 0.6% false positive rate, which isn't great, but that was with 99% accuracy. And further testing should be done. So a few of the challenges that I noticed is that DDoS attacks are a huge risk to SDN, as there's a single point of failure at the controller, and if the controller goes down, the whole network goes down. So there was a bit of research done specifically into DDoS attacks. And minimizing false positives is again a challenge. It's hard to get both accuracy high and false positives low, but you can't have the false positive rate high, or the network won't be trusted. The IDS won't be trusted. And there were some issues with the datasets, according to some authors, such as remaining bias even after the revision of a dataset. And there are also complaints about receiving data sets on new attacks late. Like if there's a new DDoS attack, it won't be immediately released to the public. It'll have to be approved before it goes out, before they can release such data sets. And there also is a drawback, an overhead on network performance. And so certain models have been designed to have minimal overhead, although they do have a cost, such as weaker accuracy. But in general, this overhead has been really ignored across most of the papers. Here are some of the common acronyms that I used, that came up. And here's a brief taxonomy. So the model type can be broken down into traditional or deep learning, and onto supervision. This can apply to deep learning as well. So a data set, supervised training is when the data set is labeled, whereas unsupervised is when you're working with an unlabeled data set. And so on to supervised methods, we have basic, such as decision tree. We have and then we have ensemble learning, which works with a collection of algorithms. So it basically looks at the results from all of them. It will use them to reach a consensus, whether it's through voting or another method. So it takes in the input from many different algorithms. And then there are also neural network methods, such as backpropagation. And with deep learning, one of the more frequent algorithms seen is multi-layer perception. And here's a quick bit of a breakdown of the common trends in author motivation. So they wish to explore a new area, they wish to improve current results, they wish to focus on either detection rate or false positive rate. They might have a great concern with DDoS attacks, like one did. And they might just wish to do simple experimentation and compare a bunch of different methods. And here are some of the metrics onto features that were used. And over here, that means that a feature selection algorithm was used instead. When I don't say that, that means that they didn't provide any information on what features were used from the data set. And a bit more information on the machine learning algorithms used, how they are categorized, and then we have the data sets that were used. We see that most methods were supervised. However, I did find one unsupervised method using Markov methods. It's a bit of like a stake diagram, and not all methods, not all information was provided, but the majority was, and we're able to see that most attempts have been towards accuracy, although some are managing to get the false alarm rate down to a reasonable amount as well. And it's one where the false alarm rate is 10%. It's pretty awful indeed, but that's for the one that has like no overhead on the network. And here are additional metrics for attack types that were used. how much was used to train it and test it when it was released, and how many times it has been cited. Here are my works cited.